Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, this is section 9.1, part C, the hardware-software interface. Okay, so far we have talked about a programmed I/O with polling and a programmed I/O with interrupt. Okay, now in either case, the CPU will be involved, of course, in the different ways. Okay, for example, if we talk about a program with interrupt, okay, program the I/O with interrupt, then we have a controller. Okay, the controller has some registers, right? Like operand, opcode, and busy register, status register, and a buffer, right? Now, for the program the I/O with interrupt, the controller has a interrupt capability. Okay, so then in order to perform the operation, so the CPU going to run a process. This process going to actually run the driver. Okay, so the first thing the driver going to check is check the busy register to see whether it's really busy, and it says, oh, I'm idle. So then the driver going to actually write the parameters, right? That include the memory addresses and other related information to the operands, and then write the opcode. Okay. Now, once this is done, and then you're going to set the busy register to busy, and then the driver going to actually block itself. It will block the current process. So now the controller going to start to copy the data from the device to the buffer, right? You're going to fill up the buffer. Now, once the data is actually completely copied from, the buffer is full, and then you're going to set up the status to, okay, the copy was successful, and then it will change the busy register to idle. Okay, and then this controller going to send an interrupt. Okay, to the CPU, and the CPU basically going to unblock the processing that was running the driver, and then the driver going to actually do this, check the status, it was successful, and then copy the data. Basically going to copy the data from the buffer to the memory location, right? Okay, so that's that. Now, if we perform these operation, the import operation, the read operation, read the data from device to the memory. Now, the chances are you're going to actually perform these read operations multiple times, maybe hundreds of times, or even thousands of times. So in that case, you're going to repeat the whole process again and again. So right now, so the next one you're going to do is, okay, so the driver going to actually check the busy register again to see whether you're busy. Now, if it's not busy, then you're going to actually, write the parameters, but it's a new parameter now, right? Because you're probably going to actually put the new, memory location, and then write the opcode, and then set the busy to, busy register to busy again, right? And then do the copy, do this device copy again. Once the buffer is full, and then you can actually set the status and change the busy register from busy to idle, and then you're going to interrupt again, right? So you can actually, if you actually perform these read operations 1,000 times, you're going to perform 1,000 interrupts. So all this is going to involve the CPU, and that's a lot of work. So then after second interrupt, then you're going to copy the data again, okay, to the memory, and then you're going to repeat this, okay, repeat this operation again, and then eventually another interrupt, and then copy the data again from the device to the buffer, from the buffer to the memory. So you're going to repeat this 1,000 times. That's a lot of work. So now in the design of new computer system, people use a new computer hardware. It's called direct memory access. So it's a direct memory access is a controller is a hardware component. It's a chip that performs the job of the CPU. It's offload the job for CPU. Okay, so that's something we can talk about next. Okay, so let's talk about the programmed input with DMA, the direct memory access. Okay, let's see. Now we have a controller here. And the controller has a couple of registers: operands, opcode, busy register, status register, and the buffer. Okay. So remember, the controller has the capability of issuing an interrupt. Okay. Okay. So now here's the I/O device. Now for programmed input, the device is most likely going to be the hard disk. Now here we have a process running the driver. Okay. Now when the device is not busy, okay, so the process running the device driver going to check the busy register and find out it is not busy, it's idle. Okay, so now the device driver going to write, perform the input operation, going to write parameters for the operation, the input operation. Okay. Now, of course, the parameters include the starting location X in the main memory. So the starting location X in the main memory should be included in the parameters. And then you're going to write the opcode, which is input operation, right? So once these are done, okay, so the controller going to set the busy register to busy, right? And then the driver going to block the process that is running the driver program. Okay. And then the controller start to copy the data from the device to the buffer. Okay. Now, once the buffer is full, now remember, if we use the programmed input with interrupt, and then the controller gonna update the status. Okay, if the copy was successful, and the status is gonna say, okay, it's successful. And then also change the busy register to idle. Okay, I'm not busy anymore. And then what's next? You're going to issue an interrupt, right? You're going to issue an interrupt to the CPU. And so the CPU going to unblock the process running the driver program. Okay. And then you're going to, read the status. Okay. Read the status and then copy the data from the buffer all the way to the memory. Okay. That's the program that import with interrupt. Now, once this is done, and then the driver going to check the busy register again, and if it's not busy, then you're going to write a next parameters to the operand and write the opcode to the opcode, right? And then set the busy register to busy, and then it just repeat the same process. Okay. Now each time it involves the interrupt, and also involves the CPU. Okay. Now to reduce the involvement of CPU, so the direct memory access controller is used. It's a hardware component. So this DMA controller is used. Now let's see how this DMA controller is used. Okay, so let's actually delete this information here. Okay, let's assume, okay, so the buffer is full, right? Now instead of update the status and then issue interrupt, then the DMA controller will be involved. Okay. Now, at the very beginning, when the DMA is used, the CPU is going to program the DMA. And so depend on the IO operation. If the IO operation, actually in the operation that the read, the import operation involves the repeated copy of data from the IO device to the buffer and from the buffer to the memory, then the CPU probably going to actually program DMA say, okay, I will ask you to perform the next 100 copies from the device to the buffer, from the buffer to the memory, for the next 100 copies, I'm not going to be involved. So you're going to actually take care for me. So the DMA is going to take care of these 100 copies. Now, the CPU is going to do this by setting a parameter called counter. So the counter could be set to 100, right? And then once the buffer is full, if the first time when the buffer is full, the CPU will not be involved. So that means the driver still will be blocked, So never going to be unblocked because the controller will not send an interrupt. The controller going to actually, basically the DMA going to take care of this copy, operation. So the DMA going to copy the data from buffer to the computer, memory. The first copy going to copy into the location X, right? Once this is done, the DMA controller going to reduce the counter, okay? Reduce the counter from 100 to 99. Okay, so buffer is also emptied, right? And then the controller gonna actually copy the next piece of data from the device to the buffer. Okay. Now once the buffer is full, and then the DMA gonna do the copy. Okay, so DMA gonna copy the data from buffer to the memory. Now each time the counter gonna be reduced. Okay, so now the counter gonna be reduced to 98. So then if you repeat this operation, so the data going to be copied from device to the buffer, from the buffer to the main memory, and this is going to repeat 100 times. Now until, so you're going to repeat the copy for 100 times, okay, until the counter reaches 0. So now, in this case, the count is 0. So now the controller then issue an interrupt. Okay, so in this case, all the data has been transferred, and device controller indicates the success failure of the operation in the status register. So now you're going to update the status register, saying, okay, the copy was successful, and then it's done. Okay, so in this case, the controller going to issue an interrupt. Okay, and then you're gonna, the CPU gonna unblock the process running the driver. So then you're gonna read, read the status, and then the resume invoking process. So that process actually running the driver. Okay. Okay, so now if successful, the driver exits and the invoking process can start using the new data in the memory. Okay, so now this time there's only one with 100 copies from buffer to the memory. There's only one interrupt that's involved. And during the copy, everything is taken care of by the DMA. Okay, there's absolute no involvement of the CPU because the driver running this operation were blocked during this time. Only DMA is actually involved. Okay, so that's the program that import with DMA. Now let's briefly discuss the difference between the polling and the interrupts. And the polling and the interrupts both result in overhead during I/O processing, but the sources of the overhead are different. Okay. Now, executing a single poll requires only a few machine instructions. Okay. So that means, but however, during that time, the CPU is 100% involved. The CPU is busy. Okay. Now, on the other hand, blocking and later reactivating the process using interrupt constitutes significant of CPU overhead. Okay. So now in that case, unless this operation takes a long time, okay, otherwise interrupt is not worth it. Okay. So in this case, so the polling is good choice for dedicated systems where only a single process is running. So in this case, there's no multi-process running. So if you free up the CPU, it doesn't help. The CPU is still gonna have nothing to do, right? So you can use the polling. Okay. Now polling is also suitable for devices that complete the I/O operation with a few microseconds. So if the operation itself is so quick, so then the driver can keep read the busy register to see, are you done yet? Are you done yet? Because the operation is going to take only, a few microseconds. So, it will quickly actually finish the job so the CPU can actually run the follow-up instructions. So the polling is good for a I/O operation, which requires a very short period of time, or a dedicated device. There's only one process. Now, interrupt, in another hand, in a general purpose multi-process environment, interrupts are better choice because if you involve multiple processes and most of the time the I/O device operation takes a little bit longer time, then so once the device is busy, and then you can actually force the driver who invoked the operation to sleep, and the CPU can actually do something else. And then once the operation is done for the device, the IO operation is done, and then invoke, send the interrupt and invoke and unblock the process that running this driver. Okay, so now let's compare the polling and the interrupts. We're going to compare these with 3 different scenarios. Now here's the first scenario. IO when polling a fast device. Okay, now here's the application, and here's the operating system, and here's device. Okay, an application program issues an IO instruction to the OS. Okay, and then which the OS gonna invokes the driver program. Now the driver gonna initiate the data transfer and starts polling the busy flag. So it start actually checking the busy register, right? And keep checking. Are you busy? Are you busy? And the device is working at this time. Say I'm busy until the device complete its job and set the busy register to idle. And then when the device is no longer busy, the driver returns control to the user application. So the driver returns the control to the user application. So then which can start the next IO operation. Now, during this time, the CPU is actually busy just working on this polling. It's just repeatedly check the busy register. So this time, the CPU time is wasted. Now, since the device is so fast, so this period of time is supposed to be very short. Okay. Now, the second scenario, the IO when polling a slow device. So device, once it's triggered, it's going to be very, very slow. Okay. So the process running the application is preempted. So again, so the application program issued an IO instruction to the OS, now which invokes the driver. Okay. So the driver, invokes the driver, and the driver initiates the data transfer, and then the driver start to pull the busy flag. And so since the driver is running now, so it's always busy. So it's busy. Okay. So because the driver is actually device going to run for a long time. Okay. So the application is preempted. Remember, in the multi-programming environment, like a time sharing. So now the process running this driver will be preempted. So the other process is going to run, okay, during this time period. And then when it's time again for this process running the driver, and then the device is still actually working on it. So when you actually pull this data, and it's still busy, okay, it's still busy, okay. So the driver continue to pull the device, but the process is preempted again, okay. So the CPU is running the other process, okay. When it's time again, okay, so this process running the driver actually get the CPU again, so the device already completed its job, okay. Okay, so the device is already completed the job, okay. So in this case, the control is actually returned to the application, and the application can issue another IO operation. Now let's take a look at this case. So during this time, the CPU time is wasted. CPU time is wasted, right? Okay. However, when the device completes the job, the CPU is running on other processes. So during this time, the device time is wasted. Okay. So that's the consequence when you try to run the polling on a slow device. Okay. So then let's take a look at the third scenario, I/O with interrupts. Okay. So in this case, okay, so again, the application issued an I/O operation, and so the operating system then still invokes the device driver. Okay, so once the driver actually initiates the data transfer, then you're gonna actually the CPU gonna actually the process gonna actually block itself. Okay, the process gonna block itself. Okay, so and the scheduler actually, the operating system scheduler gonna select the other process to run because this process running the driver is blocked. Okay, now so the device driver gonna keep running. Okay, until the device driver complete its job and update the status, and then change the busy register to idle, and then issue the interrupt. Okay. The interrupt invokes the interrupt handler. Okay. Which reactivate the driver. Okay. So then control returns to the application. So the application can issue a next I/O device. Okay. Now the CPU time is wasted in this. Okay. In executing the context switching during this time. Okay. And also the CPU time is wasted during the interrupt handler. Okay. So now device time is wasted only from the time when interrupt during the during time of the interrupt. Okay. When interrupt happens, the interrupt handler actually doing this, so the CPU is actually working on this. So during this time, the device time will be wasted. Okay. So this time until the next I/O operation is issued and the device is going to be busy again, right? So this time going to be wasted. Okay. So this is actually the comparison, okay, of polling and interrupts from 3 different scenarios. Thank you.